Throwing. Okay, we're now standing near the summit, not quite at the summit of Sugarloaf Mountain. All the rocks around here are pure, almost pure quartzite. We'll get a look at it close up down there. There's some nice looks at it. But what I want to show here is the large scale geology. This is the highest point in the Maryland Piedmont right here. Off to our west is the Frederick Valley, which is underlain partly by another Mesozoic fault basin and partly by limestone. The limestone being actually quite a bit younger than this stuff, and it does indeed contain fossils. However, there are faults between here and there, so this wasn't closely associated with those limestones to start with. And how far the faults moved, we don't know. Sometimes you can put a number on it, often you can't, and I've never heard anyone put a number on this one. But it's if I had to make a guess, I'd say it's probably 10-15 miles or so. Then on the far distance is the Blue Ridge. And the Blue Ridge is another major anticline, fairly simple anticline, but very, very large. The far side of it is overturned. That is, it's turned more than 90 degrees, and there is thrusting along here as well. So it was folded, and the fold was pushed up northwestward as well. And on the edges of the anticline is more nice, pure quartz sandstone, which stands up as a very nice ridge. It makes the high mountains over there on each side of the Blue Ridge. Beyond the first ridge here is a mass of greenstone, which used to be a flood basalt, and granite gneiss that's about 1 billion years old, about 1100 million to be exact when you use the zircon dates. Now, we're not going to get to see that on this field trip. One of my alternate field trips starts here and goes west, and you get to see those rocks close up, but I'll tell you about it anyway. That 1.1 billion year old granite is a relic of the assembly of an older supercontinent, not Pangaea, but Rodinia, which was put together by all the continents, or most of the continents, colliding about 1 billion years ago. And the gneiss that you find in the core of the mountains there has been too badly metamorphosed to say exactly what it was, but it's granite in composition. It might have been an intrusive granite, and that's the best bet, but it could also have been rhyolite. It could have been a rhyolite tuff, or it could even have been an arcosic sandstone. But all of the original texture is lost by the high-grade metamorphism that it's gone over. And rock like that is generally found deep within the Earth in a continental collision zone. So that 1.1 billion year rock records the assembly of a supercontinent. Now, how far does it extend? Well, it's found in northern Scandinavia, so it goes that far in that direction. You can find it in central Mexico. I've seen it in northern South America, in Colombia, in the core of the Sierra Nevada de Santa Marta. It's found in much of the Canadian Shield, called Grenville granites. So you find this over a very large area. As a matter of fact, it was interesting when I was in South America to look at the granite gneiss that I found there and think, oh, that's the Baltimore gneiss. Well, the Baltimore gneiss is the same thing up in Baltimore, probably separated in a rift rock and then pushed back together again when the continents came back together again. Anyway, that's the granite gneiss in the center. The overlying, you can see it sitting on it on a particular road cut that we visit, is the Catoctin greenstone. And greenstone is a low-grade meta-basalt. It's a flood basalt that originated from a crack in the ground out of which basalt magma comes and floods thousands of square miles. And this is found in areas that are under tension where the continents are breaking up. The only really good flood basalt, and that was a very small one, that's been seen by people was in, I think, 1734 Laki flow in Iceland, which killed off about a quarter of the population of Iceland. And a series of cracks, I think totaling about 17 miles long, opened up in southern Iceland, and basalt just came out and flooded the whole area. That's what happens when places pull apart. And that is dated at around 800 million years old, and that dates the breakup of the supercontinent of Rodinia and the opening up of the new ocean of Iapetus, the Iapetus Ocean, which then continued widening for the next couple of 100 million years until things turned around and it started closing again. And then things started to come together to build the new supercontinent, Pangaea. Now, here's a question. Over there on that ridge, you find sandstone very much like this, maybe the same sandstone. As I said, that's under discussion. This sandstone here is standing the highest point in the Maryland Piedmont. In between is the limestone and shale and sandstone valley of Frederick Valley. Why is this the highest point in the Piedmont? Why is this a mountain? There hasn't been any uplift here for a couple of 100 million years. This has been wearing down all that time. And that, of course, is the clue.
It's quartz.
It's quartz. It's A, hardness 7, if you remember. Mohs hardness scale, hardness 7. And B, it's chemically not quite indestructible, but next to. Whereas feldspar turns to clay. Limestone, calcite, dissolves in acid rain and is hardness 3 besides. So as this area has been wearing down, the most resistant rocks are the ones that end up standing up highest. And that's why this is standing up as a mountain in the Piedmont. If you go down to North and South Carolina, there are knobs east of the Blue Ridge. There's Kings Mountain, for example, which is a high knob in the Piedmont, made of quartzite. There's Henry's Knob in South Carolina, from which they get quite a bit of aluminum silicate mined, or they used to. Surprise, it's quartzite. So this is not unusual at all. As a matter of fact, that quartzite down there in the Carolinas may be the same quartzite as this one. Again, that's the best guess, but you don't want to put too much money in that. There are no fossils here and there are no fossils there either. But it's safe enough to say until somebody can prove you wrong. Just don't put too much faith in it. Okay, any questions as to what? Oh, if I were to continue west from here, by the way, on the other side of the Blue Ridge is the Great Valley. Here it's the Hagerstown Valley. Continues down into the Shenandoah Valley in Virginia and up into the Cumberland Valley and Lebanon Valley of Pennsylvania, and then up into the Hudson Valley and Champlain Valley in New York and Vermont. Going the other way, it's going to be the Tennessee Valley, and it's going to be the Coosa Valley in Alabama. It's all underlined by lower Cambrian limestones and dolomites, carbonate rocks, that predate anything interesting happening on this side of the Atlantic, so most of the sediments were all carbonate. But if you look at the sediments in the rock there, overlying the carbonates, you start getting periodically whole bunches of clastic rocks coming in. 3 main pulses of clastic rocks, sandstones, shales, conglomerates. Each of those pulses of clastic rock records a collision and mountain building episode along the coast where something banged into North America. For the first one, it was an island arc that formed off the coast when the ocean started closing. For the second one, it was a Madagascar-type island out in the Iapetus Ocean that banged into New England and the Maritimes. And so in that particular case, the big flood of sediments is mostly up in the northeast, such as the Catskills and the Poconos. And the third one was when Africa, South America, and Europe all banged into North America simultaneously. Africa banged into the Middle Atlantic southward down to Florida. In the Gulf Coast, it was South America that hit it, grazing the Ouachitas, for example, and the mountains in West Texas. And from New England north, it was the Madagascar type that banged into it. It's called Acadia, by the way, the land that hit. And it might have been a part that was rifted off Africa earlier, rifted off Africa, and then hit North America separately, with the rest of Africa following not too far behind. So beyond these mountains here, it's just that series of carbonates and clastics, carbonates and clastics, and carbonates and clastics, 3 sets of each, is all folded into ridges and valleys, anticlines and synclines. And where the clastics are on the surface, you get a ridge, and where the carbonates are on the surface, you get a valley. And so that's these long, long ridges and valleys that extend all the way up the Appalachians from New York State to Alabama. They continue, by the way, down into central Alabama and Mississippi, where they take a right-angle turn to the northwest. You can't see it on the surface because this is all buried by the Gulf coastal stuff. Reappears in Arkansas, goes through southern Arkansas into Oklahoma, disappears into the subsurface again just before it hits the Red River and the Texas line, circles around the central Texas hill country in the subsurface, and reappears in West Texas in the Marathon Basin as the same sort of parallel ridges, disappears again where the new mountains of the eastern Sierra Madre of Mexico hit it, except that in some places in the deep valleys of the Sierra Madre, you can again see the older Appalachian folds, Appalachian rocks, and Appalachian structures reappearing in the cores of those anticlines where the oldest rocks appear. There are traces of it down into central Mexico, but not much at all. In that 200 miles south of the border at Ciudad Victoria in Mexico, there's a nice park there where you can really see those Appalachian structures well for the last time before they're completely destroyed by the later mountain building period of the Sierra Madre Occidental. Where it goes from there, well, there are traces of it perhaps in South America, but they're not, it's really not easy to trace going on there. Too much has happened since then. Okay, I want to take one last look at those rocks down there. There's one little feature I want to show you in those quartzites.